let's start. This is a joint course with Christian Garay, and it is divided in two parts. In the first two sessions, I talk about p-adic numbers. And p-adic integration. And in the two last sessions, Christian talks about Tate-Ridge spaces and Berkovich analytification. So what is a p-adic geometry? So we can this is a theory of analytic geometry on p-adic numbers. And this theory aims to construct a p-adic analog of the complex analytic geometry, because some problems arise when we define p-adic analytic manifolds in the classical sense. For example, how to get a good analog of analytic continuation by defining analytic functions as converging power series in a ball, because in these spaces, every ball is a disjoint union of smaller balls. So Christian will talk about of two approaches to this aim. So let's start with the ground fields of this theory, that is the p-adic fields. So we will construct the p-adic fields from the point of view of absolute values. They are called also norms. So we have the following definition. We consider a field K and a non-negative real values function, okay, satisfying the following three conditions. The image of an element is 0 if and only if the element is 0. It satisfies the multiplicative property. And the triangle inequality. Then a function satisfying these three conditions is called an absolute value on K. So the pair is called a norm field. or sometimes this is called a value field. Furthermore, if this absolute value satisfying the following inequality, we say that the absolute value is non-Archimedean, and the field with this norm is called non-Archimedean field. This is called a strong triangle inequality or ultrametric inequality. And we said that the absolute value is non-Archimedean and the field is non-Archimedean field. Now we give some examples, some norm fields. The trivial example is the trivial absolute value. It can be defined for any field, and it is defined as follows. This is 1 if the element is not 0, and this is 0 if the element is 0. So this is an absolute value, and we can show that this is non-Archimedean. Another example of absolute value is the usual absolute value on the field of real numbers. And in this case, we denote it by this function. And we can look at this is Archimedean because, for example, we can consider the absolute value of 1 plus 2. And we can see that this absolute value is not less or equal than the max of the absolute values. So this is an Archimedean absolute value. Now we define the p-adic absolute value. This is another example of p-adic of absolute values. So we first fix a prime number p. And we consider a non-zero rational number. Now we recall that, that for the fundamental theorem of arithmetic, we can write this element as a product of a power of p and a rational number where the numerator and denominator are coprime with p. So we define the p-adic absolute value as p to minus r for any non-zero element and 0 if the element is 0. The exponent r is known as the p-adic order of x. So for example, if we fix p equals 5, and we consider the rational number, this rational number, then the p-adic absolute value of this rational number is, in this case, 5 to minus 1, because in the factorization in prime numbers, this can be written as 5 and we can see that the exponent 1 appears one time in the exponent of 5. So this is the p-adic absolute value of the rational number. So if we fix p equals 2, the p-adic absolute value of this rational number is p minus 2 minus 4, because the factorization of the rational number is the following. So here the two-adic order is minus 4. So as an exercise, you can show that this function is a non-Archimedean norm. On the field of rational numbers. So in addition, you can show the following. The norm of the sum of two elements equals to the max of these absolute values. When these absolute values are not equal. So what happens with the absolute values on finite fields? So if K is a finite field, then any norm on this field is non-Archimedean. Moreover, we can show that any norm of on a finite field is the trivial absolute value. So in effect, we assume that the cardinality of K is n. Then the multiplicative group has cardinality n-1. Then for any element, for any non-zero element, we have this equality. So the absolute value of this power is 1. This is a property of absolute values. We mentioned after that these properties. And then the absolute value of this element is 1. Then we can show that the norm of any non-zero element is 1, and this is 0 if the element is 0. So this is the trivial absolute value. So all the finite fields are non-Archimedean. Now we mention some properties of absolute values. The first one is the absolute value of 1 equals to the absolute value of minus 1, and this equals to 1. 2, the absolute value of an element equals to the absolute value of additive inverse, of the additive inverse. Next, any absolute value satisfies the following inequality. For the absolute value of an inverse and multiplicative inverse is the multiplicative inverse of the absolute value. And 5, if the norm of this power is 1, then the element has norm 1. Now an absolute value defines a metric function. The distance between two elements is defined as the norm of the difference between these elements. We recall that a metric function on a not-empty subset is a function on the Cartesian product of the set into the non-negative real numbers. And this satisfies the following three conditions. The distance between two elements is 0 if and only if they are equal. This satisfies the symmetric property, that is this distance equals to this one. And it satisfies the triangle inequality. And the pair is called a metric space, and this function is called a metric. Furthermore, if this distance over metric satisfies the ultrametric inequality, in this context, this means that this distance is less or equal than the max of these ones. Then we said that D, or the distance, so the metric, is called an ultrametric. And also we said that the space is an ultrametric space. Furthermore, if these distances are not equal, then we have the following equality. So we notice that this result is similar to the one given in the non-Archimedean case by replacing this distance with the norm of the elements. Now we define some examples of metrics. We have, as in the case of absolute values, a trivial metric. With this function, the distance between two elements is 1 if they are not equal, and this is 0 if they are equal. So you can show us an exercise that this space is an ultrametric space. Another example is the p-adic metric on the set of integers. We fix a prime number p. And we define the p-adic metric on the set of integers. As p2 minus r if the elements are not equal, and r is the highest exponent of p such that this divides the difference. And this is 0 if the elements are equal. With this metric, the set of integers is an ultrametric space. Also, we can obtain ultrametric space with non-Archimedean fields. So if we have a non-Archimedean field, the metric space defined by the absolute value is a ultrametric space. So in this case, we recall that the p-adic norm is non-Archimedean. So the distance induced by the norm is an ultrametric. Now we recall that the metric induces a structure of topological space on the metric space. So we can talk about topology on metric spaces, in particular on valued fields. The open balls of this topology, the topology defined by the metric, is given by the following set. Here, R denotes the radius of the ball. And A, the center of the ball. Now the closed balls are defined as the set of elements with distance to the center of the ball less or equal than the radius. The spheres are the set of elements with distance to the center equals to the radius. Now we are interested in the p-adic case. So we recall that the p-adic norm is an ultrametric. So we are interested in the ultrametric spaces, and we mention some topological properties of these spaces. So we consider X an ultrametric space. And we have the following properties. The first one is that the spheres are also open subsets in these spaces. So for the sketch of the proof, we consider a point, one point in the sphere, and we construct an open ball around this point, and we will prove that this open ball is totally contained in the sphere. So this will show that the spheres are open subsets. And for this case, we consider epsilon strictly less than R. So we recall that we take X, an element in the sphere. So the distance to the center is equal to R. And now we can take, or we take an element in the ball. Then this distance is strictly less than epsilon. So we notice that this distance are not equal. And then by the ultrametric inequality, this distance equals to the max of these ones. In the max equals to R. Then this element belongs to the sphere. And this showed that the ball is contained in the sphere. Then in these spaces, in the ultrametric spaces, the spheres are open subsets. So I think in this moment we can take a break for 10 minutes and we will continue after that. Yeah. So we were talking about topological properties of ultrametric spaces. And the first that we mentioned is that the spheres are open subsets, which is not this case is not satisfying in the real case. So, but in the ultrametric spaces, this occurs. The second topological property is that any point of a ball is its center. Again, we notice that this phenomenon doesn't occur in the real case because this is a consequence of the ultrametric inequality. So we see the sketch of the proof. And the proof consists in to take another point in a ball and to prove that this ball is equal to this one. So we notice that this ball is always a subset of this one. So this case is the trivial. And the second case follows by the triangle inequality. And this is an exercise. Now the third property. The open balls are also closed subsets. There is the basis of the open balls of, no, I mean, the basis is of open balls because they are open and closed at the same time. And this is right because the complement of a ball is the union of this sphere and the complement of the closed ball. And these subsets are open. So the complement is open and then the ball is a closed ball. For the boundary of any ball is the empty set. And this follows by the triangle inequality, and this is also an exercise. Sorry, by the strong triangle inequality or the ultrametric inequality. Thus, there are some interesting properties of the ultrametric spaces and consequently of the non-Archimedean fields. We recall that these non-Archimedean fields define ultrametric spaces. Also in the metric spaces, we can talk about Cauchy's sequences and completions of the spaces. So in terms of absolute values, these concepts are defined as follows. Then we have the following definition. A sequence in the field K is convergent to an element in K in the field if for any epsilon there exists a natural number such that the absolute value of this difference is strictly less than epsilon for all n greater than capital N. This is similar. We can notice that this is similar to sequence in the real case now. But in this case, we are considered a more general absolute value on any field. So if this happens, we're using this notation. Or we say that this limit the limit of this sequence is this. So if there not exists such limit, then we say that the sequence is divergent. Now a Cauchy sequence is a sequence such that for any epsilon, there exists a natural number such that the absolute value of this difference is strictly less than epsilon for all nm greater than capital M. So it is now difficult to see that if we have a Cauchy sequence, then the sequence of absolute values is also a Cauchy one in the field of real numbers. A sequence is said to be a null sequence if its limit is 0. Fourth definition, we said that a norm field is complete with respect to its absolute value. If any Cauchy sequence has a limit in the field. This means that any Cauchy sequence in the field converges to an element in the field, in the same field. Now a completion So let me use a new slide. A completion of a normal field is a field K hat with an absolute value and an injective field homomorphism on K into K hat. Such that the norm on K hat extends to the norm on K This means that the norm of the elements in K equals to the norm of the image under this homomorphism of the elements in K. Also, this satisfies that the image of this function is dense in K hat. And finally, K hat is a complete field. So if a field with an absolute value satisfies these three conditions, then we say this is a completion of a norm field. So for norm fields, the completion always exists. So the following theorem establishes that we can complete any norm field. And furthermore, this completion is unique up to isomorphism. So we can construct a completion as follows, one completion as follows. First, we consider the set of Cauchy sequences. And we denote it by capital C. We recall that we have valued field fixed. So this is a set of Cauchy sequences in K. So we can show that this set is a commutative ring with the following operations. So we can add sequences by adding term by term. And we can multiply them in a similar way. So this is a good exercise to prove that these operations are well defined. I mean, we need to prove that the result of the addition and multiplication are Cauchy sequences. And furthermore, this is a ring with identity, multiplicative identity. This identity is the constant sequence of ones. So I forgot, this is an exercise also to show that this set of Cauchy sequences is a ring, a commutative ring. So now we notice that the set of null sequences is a maximal ideal of the ring of Cauchy sequences. We recall that the null sequences are the sequences converges to 0. Then, and since this is a maximal ideal, the quotient is a field. So we will prove that the completion of K is just this quotient. So in this case, the injective function is defined as follows. The image of any element in K is the constant sequence of A's. So as an exercise, prove that this function is injective, and also this is a field homomorphism. So we need to define a norm on k hat, and it is defined as follows. Before that, we recall that the elements of k hat are cosets with representatives in capital C, which are Cauchy sequences. Thus, any element on k hat has the form, a representative, a Cauchy sequence, plus the ideal. Or we can denote it with this simple form. Then the norm is defined as the limit of the absolute values of the terms in the Cauchy sequence. Now we notice that this norm, this function is well defined because this limit is a real number. So we recall that if this is a Cauchy sequence, then the sequence of norms is a Cauchy one, but the field of real numbers is complete. Then the sequence converges to an element, to a real number. Moreover, this real number is greater or equal than 0 because all these terms are positive or 0. Then this function is a real value function on k hat. Now, now we need to prove that this norm of this function is well defined. That is, it doesn't depend on the representative. I mean, if we have two cosets, equal cosets, then we need to prove that the norm of this coset equals to the norm of the second coset. And also, you can prove that this function is a norm on k hat. Now we can see that this function extends to the norm on k because of the form that we see k into k hat. So we recall that any element any element of k has the form a constant sequence in k hat. Then the norm of this constant sequence, by definition, is the limit of this constant. So this is constant, the constant. Then this shows that it extends to the norm on k. And also you can prove that with this identification, k is dense in k hat. And k hat is a complete field. With respect to this norm. So with these properties, the quotient denoted by k hat with this norm is the completion of this value field. So we define the field of p-adic numbers as the completion of the field of rational numbers with the p-adic absolute value. And this field is denoted by QP. In this case, we denote a norm of Q on QP with the same notation as in the rational case. So I think that's all for today, and we'll continue tomorrow with p-adic integration in the second part of this section.